Good afternoon, everyone.
Good afternoon, Mr. Allen. I want to apologize ahead of time. Right now, I have people working on my bathroom. I may have to go back and forth between them and here.
Okay, all right. Okay, folks, so just taking a moment to get everybody logged in here. Okay, welcome back, everyone. Hey, I hope you had a nice Labor Day weekend. At least, Sunday was a little ugly with the weather, but Saturday and Monday were pretty nice. So I hope you had a moment to take for yourself. So we're going to jump right into chapter 2, chemistry chapter. I need to figure out where you are as a group with your chemistry knowledge, because chemistry is not a required course, not a required prerequisite for this course, but if you've had some chemistry, it can make life a little easier. So before I continue, are there any concerns about submission of lab work or anything like that? Is everybody okay?
I do have a question. We were discussing it with some of the girls. So we were wondering if it matters or if there's a difference if we measure the microbes from the screen or from the printouts. Would we have different measurements if we print them out?
Oh, as long as you do it consistently, it should work out. Like if you're measuring things on the screen, then you should do everything from the screen. If you're measuring from the printout, you should do everything from the printout. Don't go back and forth between the two.
Okay. All right. Thank you.
Okay.
Professor Allen, I'm having trouble. I got stuck on the 5th part, so maybe after class, if I can kind of touch base with you one-on-one, I would appreciate that.
No problem, Elena. Just as a general comment, I will have office hours 2 to 3. I'm happy to help anybody that might want a little help. Okay, so okay, I'm going to jump right in, folks, because we don't want to get behind early in the semester. So I'm getting my desktop ready for you guys. And here we go. Okay, so we're in chapter 2. All right, so let's start with a definition for chemistry. Okay, we could define chemistry many different ways, but we'll start with a simple statement. Chemistry is the science that studies how atoms and molecules interact. I think that may not be completely comprehensive, but it's a pretty good starting place. Chemistry is the science that studies how atoms and molecules interact, okay? Now, obviously, that doesn't mean too much if you don't know what an atom is or a molecule is, so that's what I need to figure out where the average knowledge of this group is as we continue forward. Okay, if you've had some chemistry, even in like A&P, that'll be a good foundation for what you're doing here. Okay, just because we're studying microbiology doesn't mean you throw out all your chemistry knowledge from A&P or another course that you were taking, right? Even if you took inorganic chemistry, Chem 1, Chem 2, 101, 102 here at Hack or someplace else, the same basic principles apply, right? Microorganisms work off biochemistry, just like every other living kind of thing on the planet does. So if you have any chemistry background, you will be okay. Okay, you will be okay. All right, so let's start with the basics. Let's talk about, atoms. Okay, atoms are the fundamental units of matter. Okay. I'm on pages 24 and 25 of your textbook at this time. If you have your textbook open, that can be helpful, pages 24 and 25. Okay. Now, we can think of atoms as many different things. One very loose definition, I like to think of atoms as the Lego bricks of the universe, right? Think about it. Everything that you could pick up and hold in your hand, where it's a pack of sticky notes, whether it's some notes, whether I'm touching my shirt, my hair, my textbook, whatever it might be, a glass of water, all this stuff is made of atoms, matter, and matter's made of atoms. Atoms are the Lego bricks. Maybe you have some Legos at home that you play with your children. Maybe you still play with Legos. That's okay, right? Because Legos can be fun. So atoms are the Lego bricks of the universe. And what I mean by that is just like you take Lego bricks and you link them together in different arrangements and patterns, you build larger things, right? You build molecules, which then can be used to build, organelles inside cells, which then can be used to build cells, which then can be used, to build tissues if we're talking about animal biology. So the Lego bricks of the universe, right? You can connect atoms in different arrangements and patterns to build molecules compatible with life. Okay. All right. Please stop me along the way if you want to ask a question. I want to really roll here. Okay. So please ask away. Molecules. Molecules are collections of atoms that stay associated by chemical bonds. Okay. Let me ask a question in the chat window. Okay, question coming through. Is a chemical compound also a molecule? What do you think, folks? Okay, so it seems like we generally have the general average answer says yes, maybe. Okay, all right. So, all right. So yes, a compound is a molecule, and what makes it a compound is the fact that there's two different types of atoms present. Okay, so chemical compounds are molecules which have at least two different types of atoms present. Okay, so Kit says every compound is a molecule, but not every molecule is a compound. Beautiful statement, Kit. You're absolutely correct. Absolutely correct. Okay, so for example, okay, H2O, right? Water, if I could type properly, right? Water, okay? Water is a molecule. And it is also a compound. The reason it is a compound is because we have at least two different types of atoms present. We have hydrogen atoms and we have oxygen atoms. So it's a compound, okay? We could have the kind of oxygen that we're all inhaling into our lungs, several times a minute. So we could have atmospheric oxygen, which is O2, right? It's diatomic, okay? So O2, this is a molecule, but it is not a compound. Right? It's not a compound because there's only one kind of atom. Yes, there's two atoms, but they're both of the same type of atom. They're both oxygen atoms. So this is not a compound, okay? All right, any thoughts, questions? Okay, all right, so, most people go into biology because they really would like to avoid chemistry. They really would like to avoid physics, and they would like to avoid math. Folks, we can't do it, okay? To do useful biology, we have to think about chemistry. Sometimes we got to think about physics, and we definitely have to think about math too, okay? So biology is a science, the language of science is math. We're going to encounter that as you already did with your first lab activity, right? So, okay, let's talk about the fundamentals of atomic structure. Now, I'm not a physicist, and I'm sure a physicist could give you a better lecture on atomic structure, but this is just so you have some foundational knowledge. Page 25, figure 2.1 there. You can see that a typical atom has a nucleus in the center, and outside the nucleus, you have these electrons that are moving around all over the place. The picture on page 25 is very static, right? It's every object in figure 2.5 is sitting still. It's not in motion, and that's really not reflective of the dynamic nature of matter and life on our planet. Everything is dynamic. So the best we can do in textbooks is give you a shadow of reality, a shadow of reality. Okay, so atoms, as you know, are made of subatomic particles. Okay, atoms are made of subatomic particles. And we'll define them here for you. You know that there are protons. Okay, these have a positive charge, and they are found in the nucleus of the atom. We have neutrons. They have no charge. They are, in fact, neutral, kind of like Switzerland, but these are also found in the nucleus. Okay. And we have electrons, right? Thank God we have electrons, or we wouldn't have electricity, so to speak, at least not as we understand it. So we have electrons. These have a negative charge, and they are found outside the nucleus of the atom. Okay. So please be a little bit careful. What I find is that sometimes new biology students get confused between the nucleus of a cell and the nucleus of an atom, right? It's one of those words that, depending on context, the context of the conversation, you can get confused about what we're talking about. Okay, so just be careful there. Okay, careful not to confuse the nucleus of a cell with the nucleus of an atom. Okay. All right. So, okay. All right. Let's continue again. Okay, so here's a question. I'll put the question in your notes and then we'll answer it, okay? Okay. Go ahead and type the answer into the chat window if you know, or if you want to speak up, you're feeling like you want to talk today, go ahead and unmute your microphone. What characteristic of atoms do scientists use to tell different types of atoms apart? if I had a carbon atom in my left hand and a nitrogen atom in my right hand, how would I know they're different atoms? How would I know this? Okay, so I'm looking at the chat window here. Okay. All right, so I got a couple different answers here. Number of protons in the nucleus and atomic mass, protons and neutrons, electron. Okay. All right, so I'm getting answers, and if you look at the responses in the chat window, you can see that they are not equal to each other. There are differences. That means there is a disagreement amongst you about what characteristic is most commonly used, okay? So the correct answer is the number of protons in the nucleus that Kit started with. That's the atomic number, right? The atomic number. Okay, so let's define that. Okay, atomic number is the number of protons in the nucleus of an atom. All right, so this characteristic is what scientists use to distinguish, to tell apart one type of atom from another, right? The different elements of the periodic table can be distinguished because they all have different atomic numbers. Okay, if you would, please turn the page in your textbook to page 26. Okay. So let's take a look at table 2.1 there. Table 2.1 there. Okay. So let me ask you in the chat window. Well, you know what? I'd like to talk to some of you folks here today. Okay. So let's see here. So folks, I'm going to just call on a few people. Don't be shy. Don't get nervous. This is a friendly place. It's totally okay for you to get something wrong. I'm not going to bite your head off. Okay, so just participate. Okay, so Odalis, could you please unmute your microphone and say hi to us?
Hi.
Hi, Odalis. Odalis, do you have your textbook open?
No, I'm looking for it right now.
Okay, all right, folks. And this is not just for Odalis, this is for everyone, right? I do expect that your textbook's open in front of you when I'm talking to you, okay? You never know when I'm going to feed a question your way. All right, so we're going to move on since Odalis is looking for her book. All right, let's continue here. Michelle Lee. Michelle, can you please say hi?
Hello.
Hi, Michelle. Do you have your book open?
Yeah, but I don't know which page we're going
Okay.
on.
Please turn to page 26. Page 26. Should be table 2.1.
26. Okay.
Yep.
Okay, I see the table.
Okay. All right, Michelle. So Michelle, can you tell me what the atomic number of oxygen is?
Oxygen is 8.
Okay. So here's another question for you, Michelle. Can you please tell me how many protons are in the nucleus of an oxygen atom?
How many protons?
Yeah.
Is it 8 also?
It is. Very good. You see, I just asked you the same question 2 different ways, right?
Mm-hmm.
Everybody might experience that on the exam where I ask you the exact same question multiple different ways to see if you're really picking up on the concepts. Good job, Michelle. All right. Okay, so the atomic number of oxygen is 8. You can see that, okay? Very good. All right, so, you know, if we all took a field trip to the local zoo, let's say we went to Zoo American Hershey, right? We would be able to tell the various animals apart the wolves, the eagles, the bears, the lions, everything they've got, we'd be able to tell them apart because we can visually see that these animals are in some way different in appearance from each other. Their shape, their size, their coloration, they're different. But with atoms, we don't have that luxury because they're way too small for us to see. So a characteristic had to be defined and focused on by scientists to tell atoms apart. And the most simplistic characteristic they came up with was the atomic number, the number of protons in the nucleus of an atom. Your textbook doesn't give you a periodic table of elements inside the chapter, but if you remember that horrific thing from high school chemistry class, our universe is made of atoms, different kinds of atoms, and there are no two atoms on the periodic table. There are no two elements on the periodic table that have the same atomic number. In fact, if you look at table 2.1, you can see that every element listed as an example has a unique atomic number. And that's important that you can appreciate that. That's how we tell different atoms apart. Okay, please shoot away if you got any questions. All right. So here's a question. Where are atoms manufactured? Where are they manufactured? This is a sneaky way of asking you, where is matter built? Where is matter built? All right. Let me ask you a question in the chat window. Okay. Here's a question in the chat window. Have you had a college level chemistry course? Okay. All right. All right. So some of you, the answer is yes. Some of the answer is no. Don't worry. I promise you I can get you through this, even if you haven't done that. I promise you. Okay. So Kit, you have a comment in the chat window. Isn't it that matter isn't created or destroyed? No, Kit, that's energy. Energy is not created or destroyed, not matter. It's different for matter. Okay, so where is matter created? Okay, Fatimata, I like your answer. It's not correct, but I like it. I mean, you're thinking bio here, okay, or maybe you're thinking the nucleus of chemistry. Okay, all right, folks. Rather than belabor the point on this, I'm just going to tell you, the most common place you're going to find matter manufactured is in the nuclear processes that take place inside stars of our universe. Stars. Nuclear processes that are taking place inside stars is where matter is first constructed. When I say nuclear here, I'm talking about the atomic use of the word nuclear, not biology, right? Nuclear processes that happen inside stars that require incredible amounts of pressure and temperature for them to take place, okay? Kind of pressure and temperature you're not going to find here, at least on the surface of our planet, okay? So think about it. All matter in the universe, as far as we can tell at this moment in time, originated at some point in some kind of star process, which means all the atoms inside your body originated at some moment through the vast cosmic time of space in a star. And I use this to tell you that you literally are made of star material. That is no joke. You are made of star material. Everything on our planet is made of star material. Okay, so, all right, let's continue. Let's continue. Thoughts, questions? Hang in there, gang. This is the only chemistry chapter in the course, and so if you're feeling a little bit uncomfortable, we can get you through it, I promise. All right, so atomic number is the number of protons present in the nucleus of an atom. There's some related concepts of which some of you answered questions in the chat window that tell me you're reading and thinking, and that's fantastic. Okay, let's start with this one. Mass number. Okay, mass number. You'll notice on table 2.1, the fourth column says approximate atomic mass. In other words, to make the table kind of short and sweet, they rounded some things, and that's okay. But you see atomic mass, which is not quite the same thing as mass number. Okay, there's mass number. Maybe I'll do it this way: mass number versus atomic mass. Okay, because these things are not identical, but they are in fact related to each other. Okay, so mass number is the number of protons plus neutrons present in the nucleus of one single individual atom. One single individual atom. The number of protons plus neutrons present in the nucleus, one single individual atom. A related idea, which is the fourth column of table 2.1, is atomic mass. Okay, for those that have been around a while, or maybe you've been reading some older textbooks, atomic mass used to be called atomic weight. Technically, they're not quite the same thing, and these days we don't use atomic weight with beginning students because we want to teach you the best way we can. Okay, so atomic weight is an older deprecated term that you may have encountered in the past. Atomic mass is the average number of protons plus neutrons present in the nuclei of a group of atoms. Okay, so when you think about mass number versus atomic mass, the key difference is mass number is worried with the number of protons and neutrons in one individual atom, whereas atomic mass is the average number of protons plus neutrons in the nuclei of a group of atoms. Okay. All right. So, atomic mass is concerned with averages, which if you're going to have an average, you typically need to have more than one because we're talking about a statistical concept. Okay, so groups of atoms here. All right. So here's a question that we'll put into your notes. Can two atoms, for example, two carbon atoms, be the same atom yet have different mass numbers?
Yes.
Okay, thank you. All right, love it, love it. Okay, so Tiffany is asking in the chat window, is anyone else having a hard time? I guess, Tiffany, you're looking at the digital electronic version of the book. Is anyone else having a hard time with that?
My electronic book is fine.
It
Okay,
keeps telling
thank
me that it's not a private connection, and I don't know how to fix it because I've downloaded Fox browser or whatever that Fox internet is, and it's not working. It won't let me connect to it.
You should be using Chrome.
I have Chrome, and that's what's telling me that it's not a private connection or something, and it's not letting me access it.
Okay. So Dallas, you're having the same problem. Okay. So Tiffany or Dallas and anyone else, I can't troubleshoot that at the moment, but let me remind you where you go at Hack to get help with those kinds of issues. So let me show you this. And I'll just bring it up right here. Okay,
I'm
so
sorry, I don't mean to interrupt your class.
I'll just do this quick and we'll move on. So thank you. I don't want you to feel like you're left out or struggling, but you might have to troubleshoot some of this with our tech people. On the Hack main web page, you go to Learning Commons, and Learning Commons has user support. So I would encourage you, if you're struggling to get access to your book, to call 717-780-2570 after class today and make sure that they solve your problem for you, okay?
Thank you.
You're welcome. Okay. Yeah, we're definitely dealing with technology issues these days. So let me get back to the original question in the chat window. Can two atoms, for example, two carbon atoms be the same atom yet have different mass numbers? And I think we got there, right? We said, yes, we could have isotopes, right? Chelsea typed isotopes into the chat window. So that's a definite yes, okay? Yes. So in other words, what I was trying to fish for with my question, some atoms have isotopes, which means there are different versions of the same type of atom. For example, okay, okay, so the word isotope is on page 25 of your textbook, left-hand column down at the bottom, For example, two common isotopes of carbon are carbon 12 and carbon 13. And so I'm going to ask some questions here. Okay. All right. So let's see here. Okay. Lance Brosey. Lance, can you say hi to us?
Hello.
Hi, Lance. Lance, do you have your book in front of you?
Yes.
Okay. So Lance, on page 26, okay. Lance, I'm going to ask you a first question here. Lance, how many protons are in the nucleus of a carbon atom? Okay, so let's see here. Lance, how many protons are in the nucleus of a carbon atom?
4.
4. Okay, no, that's not correct. I'm curious, what caused you to answer that?
I was just looking at the table.
Okay, so let me ask you a question. In the table where you see the first column, it says element, and there it says carbon. If you go to the right, what is the very first thing you see?
Shell electrons.
Okay, so we are not looking at the same table. Are you looking at table 2.1?
I was looking at 2.2.
Yeah, there's the problem. Okay, so let's do this again. So Lance, how many protons are in the nucleus of a carbon atom?
6.
Okay, so Lance, if you have a carbon 13 atom, and I'm going to type this into your notes here, okay? We have a carbon 13 atom, Lance. How many neutrons are present in its nucleus? Just for the benefit of everybody, if we have a carbon 13 atom in which we know there are 6 protons present because we know the atomic number is 6, then how many neutrons are present in the nucleus of that atom?
7.
Okay. Yes. All right. Absolutely. So Chelsea, could you please just explain to everyone how you came to the number 7?
Sure. So carbon, like straight across the park is going to have 6 protons. A carbon-13 is going to be 6 plus 7, so it'd be 7 neutrons. Your neutrons will change, your carbon protons will not.
Yes, that's true. And let me just communicate that slightly differently. If you're looking, Lance, if you're looking at page 26, table 2.1, okay, right? If we're dealing with carbon-13, and we know that there are 6 protons present, then to answer my question, what do? You take 13 minus 6, and you end up with 7, right? There are 7 neutrons present in the nucleus. Does that make sense, folks? Are you okay? All right. Anybody want to ask a question at this time? Okay, all right. Well, you let me know if you have questions. And remember, as you do your studying, I'm going to encourage you very much to try to answer the practice questions on page 49 and 50, right? The answers to those questions are in the back of your textbook, so you can practice and then check your work. It's an important thing to do while you're preparing for the course. Okay, all right, so we now have the basic fundamental characteristics of atoms defined, which is the atomic number versus the mass number versus the atomic mass. Okay. We could talk more about isotopes, but I think I won't at the moment. If you remember from anatomy and physiology, isotopes are really very useful in a clinical setting to help identify disease tissue, such as the location of a tumor or some other kind of disease tissue in the body. Okay, I'm going to jump, rather than sitting here defining terms for you, I'm going to talk to you next about chemical bonds. Okay, chemical bonds. All right, so you see on page 27, 28, maybe a little bit on page 29, that your book is talking about chemical bonds, right? Chemical bonds are probably the most interesting aspects for biology because cells and viruses are made of molecules, and molecules are groups of atoms that stay connected to each other by chemical bonds, okay? And you read a typical introductory textbook and you think, okay, there are 3 types of chemical bonds. They are ionic, they are covalent, and they are hydrogen. Well, those that have had a formal chemistry course, you know that there are actually some other types of chemical bonds, such as van der Waals interactions and hydrophobic forces. That being said, we will stick to the foundational knowledge of this chapter. Okay. Okay. So chemical bonds, I know. What are chemical bonds? What are chemical bonds? Well, they are attractive forces, invisible attractive forces, right? Attractive forces, invisible attractive forces that hold atoms close to each other. Okay. What types of chemical bonds are there? Well, we have ionic, covalent, hydrogen bonds, and we're going to talk about all of them. But before we talk about all of them, I want to talk about a way of thinking about the bonds. Okay, so when you read a typical textbook, you'll come away and say, okay, I get chemical bonds. There's ionic bonds, covalent bonds, hydrogen bonds. They seem like there's just different types of attractions. Okay, different types of attractions, and that's true. But what students often focus on is that they are different. Well, I want you to flip that on its head. They're not really different. They're not really different. They're actually quite a bit the same. They're quite a bit the same, okay? So consider the following analogy. Okay, consider the following analogy. And I'm going to just do a little quick drawing here. Sometimes I'll do that. I might make things worse, who knows, but we'll try it anyway. Technology is so brittle. Okay. All right, so consider the following analogy. Here is a triangle, right? Maybe a poorly drawn triangle, but it is nonetheless a triangle. And so the question I would pose to you is this. Okay, and I'll put this in the chat window here. Here it comes. No matter which side of the triangle, left, right, or bottom that I point to, am I referring to the same triangle? If I did this, folks, if I did this with my drawing here, hold on a sec. If I did this and pointed to the left, and then pointed to the right, and then pointed to the bottom. Okay, I see your responses in the chat window. Okay, obviously teachers are sneaky. Sometimes we're fishing for specific answers. It's not always obvious to students what that is, but you get the idea. Yes, I'm referring to the same triangle. Well, chemical bonds are kind of like this. And what I'm suggesting to you is, while there are different types of chemical bonds, they're basically three sides of the same triangle. Okay, so in other words, I would, to continue and complete the analogy here before I take more notes, is that, maybe the left side is ionic, and I'm not drawing this in any specific way, ionic, covalent, and hydrogen. Okay, so ionic, covalent, or hydrogen are like three edges that refer to the same triangle, three edges that refer to the same triangle. Okay, and let's see here. Okay, so let me put some language on this. Okay, let me put some language on this. The different types of chemical bonds are very related to each other. They are three sides of the same common triangle. Okay, and so, what is it that these bonds have in common? Okay, what do these bonds have in common? What they have in common is that they all refer to a level of attraction between positively and negatively charged particles. What are those positively and negatively charged particles? They are protons, positive, and electrons, negative. What do these bonds have in common? A degree of attraction between oppositely charged particles. Okay, protons attracted to electrons. All right, so if these bonds have this thing in common, a degree of attraction, why do we even bother labeling the three bonds as three different types of bonds? Okay, the difference is not due to the attraction. The difference is not due to the attraction. The difference is due to how powerful the attraction or how weak the attraction is. Okay. These bonds all involve a different magnitude of attraction between oppositely charged particles, okay? A different level of attraction. Okay, so let me ask you this and then I'll let it rest, okay? In the chat window. In the chat window, here we go. What is the common idea between the following words? Pudgy, overweight, obese. Pudgy, overweight, obese. Okay, so fat in a broad sense, so you might be referring to adipose tissue or large, heavier than a set weight. Okay. All right, so many of you are approaching in here. What I'm trying to get you to see is, and I'm not using this analogy or example in any way to shame anybody. That's not my point here. My point is this, that you might be at the shopping mall and you might see somebody that's carrying a little bit too much body weight. And so you might call that person pudgy. And then you might look further down the shopping mall and you might see someone that obviously has a weight problem. They're carrying way too much body weight to be healthy. And so you might say, well, that person is clearly carrying way too much body weight. So I don't want to use the word pudgy. I want to use the word obese. So pudgy and obese are at different ends of the spectrum, right? Kit in the chat window, all referring to excess weight, but referring to varying degrees of excess weight. I love that. Yes, absolutely. That's what I'm trying to suggest to you. Okay, so these words we're using here to describe how much, too much body weight a person is carrying refers to different magnitudes of too much excess weight. Same thing with these different types of bonds. These different type of bonds refer to different magnitudes of attraction, So, okay, let's take and make a nice table here. Nice, my document would work here. Okay. All right, let's do this. Let me put a table in your notes. That is basically 3 columns, 4 rows. And in this, we will have the type of bond. We will have the strength of the bond. And in the 3rd column, we will have the length of the bond. Okay. And we could put numbers on these things. I mean, numbers, things have been measured by chemists over the years, so we could do that, but I'm going to keep it very generic right now. And we're going to put in ionic, covalent, and hydrogen bond. And so I want to ask a couple questions in the chat window. Okay. And here it comes. What type of chemical bond has the strongest attraction between oppositely charged particles? Interesting. Okay. I'm very interested that I'm getting the answers that I'm getting. I'm very interested by that. Okay. It turns out as you look over the spectrum of answers that we're getting, right, we got them all up there, right? The answer is actually covalent. Covalent bond has the strongest attraction. Okay. Covalent bond is the strongest. Hydrogen bond turns out to be the weakest, and ionic bond's in the middle. Ionic bond is like the middle child of the family. Okay. All right. Now you may not understand why this is true right now, but we're going to work on that. Okay. Does ionic get disqualified because it's technically a trade? Oh, I see what you're saying. I don't know how a chemist would answer that, Kit, right? Donating electrons, right? I think probably the quickest answer I to give you is I think, yes, that's what a chemist would say to you, right? When an atom donates away an electron to create the ionic bond, the original atom that donated does not get the benefit from any of the attraction of the electron that it gave away. So I think yes is probably the simplest, quickest answer I can give you on that. Other questions? All right, so next question. In the chat window, here we go. What type of chemical bond is longest? If you were to measure the distance with a tiny little ruler between the nuclei of the two atoms that are connected by the bond, which type of atom would have the longest bond? Okay, so we're getting one response with a question mark. How about the rest of you? Okay, all right. Okay, so here, if you look at the community of answers here, we are getting more of a consensus, are we not? And in fact, hydrogen bond is correct. Okay, the hydrogen bond is the longest bond. Covalent bond is the shortest. And ionic bond is middle. So ionic is middle for the categories we're considering. If this is bothering you right now, you're like, I don't know what he's talking about. Well, hang in there, gang. We have much more to do. But let me say this as an analogy. You know, if a hydrogen bond is the weakest bond, then it kind of makes sense that it should have the longest bond length, right? If the ability of my two hands to be attracted to each other is very weak, that means they're not going to be very strongly attracted. So they should float apart from each other. So that should create the circumstances for the longest bond. Okay. In a different analogy, maybe this will work for you if the first didn't. Think about last time you had a relationship where you dated somebody. You know, generally speaking, is it easier to have a relationship with somebody that lives in the same geographic area you do, or somebody that lives in another state? I mean, I think you would agree that it is harder to maintain a long distance relationship, long distance being the length of the distance between you and the person in another state. So the strength of your attraction is weaker. It's harder to maintain a relationship when you're further away. When the attraction is weak, you're further away, longer the bond, okay? All right, thoughts and questions before we continue? Okay, all right, let's start defining the bonds, okay? So we've listed them out, but we haven't defined them yet. So, okay, bond definitions. You know, talking about this stuff is difficult. Learning about this stuff is difficult because you really can't see atoms. You really can't see molecules. Yes, you might find a cartoon of somebody talking about a glucose molecule, but that's not the same thing as really seeing it with your own two eyeballs. So you have to use more of your mind to imagine how this stuff is actually working. And that's a challenge when you're not used to that. All right, so let's start talking about an ionic bond first. An ionic bond is an attraction created between atoms when one atom donates, or if you prefer the word, transfers one or more pairs of electrons to a neighboring atom. The example that we'll use, and honestly, I do get tired of talking about it, but it's what all the beginning textbooks use, is the sodium chloride example, figure 2.2. Okay, so all of you know that sodium chloride, I'll just put it out in words, right? This is table salt, right? You ate some table salt and whatever food you had for a lunch break before class today, you had sodium chloride, very likely. Okay, sodium chloride is a compound. Okay, this is a, say, chemical compound. Okay, but the broader question we're trying to address at this time is that sodium chloride is a chemical compound. It's a molecule. It's got two different types of atoms that are joined by a bond. Well, why does this bond form? Why does the bond form? That's what we need to address here. Okay, that's the question. Why do sodium and chlorine atoms become attracted to each other? And, again, I really, without a doubt, a chemistry professor would be able to explain this better than I can. But this is just beginner level material. So let's see how badly I can mess this up for you. Okay, I'm talking tongue in cheek because I don't intend to mess it up for you. All right. So I'm going to try to walk you through a process that allows you to understand this on your own. I'm going to try to give you what you need so that you can reason your way to your own understanding about why sodium and chlorine atoms are actually attracted to each other. Okay, so if you do have your textbook, I'm going to ask you to turn back to page 26, table 2.1, because we can use that to help answer this question: why are these atoms attracted to each other? Okay, and so excuse me a moment while I get a lozenge. Spend too much time talking, mouth gets dry. Okay, here we go. So I can answer this best, I believe, if I draw. So we're going to go back to a drawing. And what I'm going to say here is, if I have a sodium atom and a chlorine atom, notice that I'm intentionally drawing them as separated from each other. I'm suggesting at the moment, through their separation, that they're actually not bonded. That's what I'm trying to suggest through the separation of these atoms being drawn. Okay. All right, so let me see here. Aubriana Sanchez. Aubriana, could you say hi to us?
Hello.
Hi, Aubriana. Aubriana, do you happen to have your book open in front of you?
Yes.
Okay, so on page 26, table 2.1, I'm going to ask you some questions for the benefit of everyone, and let's see what we can do with this. So Aubriana, here's my first question. Aubriana, how many protons are in the nucleus of a sodium atom?
11.
Okay, thank you. That was a beautifully correct answer. And what column of the table did you read that from?
In the third column.
Okay, what is the heading of the third column?
Atomic number.
Thank you. Okay, so we got 11 protons. I'm going to list that out as 11 with a plus sign indicating the protons, right? Okay, so Aubriana, if a sodium atom has 11 protons in its nucleus, how many electrons is it going to have orbiting outside the nucleus?
11.
That's right. Do you know why it's right?
Why? Is it because they're both the same? They have to be equal?
Why do they have to be equal?
Because I don't know. Cancels
Aubrey-
it out, like it makes
Oh.
it.
Yes, okay. Aubriana, you did a fantastic job. Pat yourself on the back, okay? You did a good job. All right. So, so what was Aubriana saying there? What she was saying there, for the benefit of those that don't know and have not had chemistry, that all the elements on the periodic table of elements, including information on table 2.1, the underlying assumption here is that atoms are defined as electrically neutral. They're defined as electrically neutral. Well, why are they defined that way? Well, that's what chemists decided to do many, many, many decades ago when they were designing the periodic table of elements. This is a way of thinking about things. So the sodium atom has 11 protons, 11 electrons. It's electrically neutral. If you stay with me on this, okay, so Rachel Spittle. Rachel, could you please say hi to us?
Hello.
Hi, Rachel. Rachel, how many protons does a chlorine atom have in it?
17.
Okay, beautiful. So Rachel, that has 17 protons. And so how many electrons does it have?
17.
Okay, you got it. Okay, thanks, Rachel. So if we have sodium and chlorine that are both electrically neutral, they're never going to interact with each other, are they? If they remain neutral, these atoms will not interact. So the question becomes, what causes these atoms to lose their neutrality? What causes these atoms to lose their neutrality? And I'll give you the quick answer and then point it out in the textbook. The quick answer is this. Atoms, their structure requires them to have a certain composition to the electrons that orbit around the nucleus. And if that composition is not balanced the way that they're supposed to be balanced, electrons are ejected from an atom, and in some cases, electrons are accepted from another atom. Okay, I'm talking about the electron rings of figure 2.2. The electron rings of figure 2.2. Okay, page 28. All right. Okay, so let me see here. Yasmin, can you please say hi to us?
Hi,
Hi, Yasmin. Yasmin, do you have your book open?
yes.
Okay, so on page 28, figure 2.2, picture A, the top left corner, Okay, so Yasmin, in the top left corner, how many rings of electrons do you see? How many electron rings do you see?
Is it for hydrogen? Or which
No,
one?
top left corner of page 28. Figure 2.2.
Sorry. Okay, for the sodium atom,
Yes.
2, 4, 6, 8. 11, but then it loses one.
Okay, so you're in the right ballpark, but listen to my question again. How many rings of
Oh,
electrons do you see?
Okay. Is it 3?
It is 3, absolutely. And so your previous answer was what I was coming to next. Do you notice that in the third electron shell, there's only one electron when that atom would really be most stable if in fact there were 8 electrons? Does everyone see that? And so what is your book trying to show you? Because sodium atom does not have an outer third ring of electrons which is entirely filled, it's unhappy, it's unstable. And so to become stable, what will sodium do? Sodium will eject an electron. You did good, thank you, Yasmin. Okay, so what causes these electrons to lose their neutrality? Okay, let me write the answer down here. What causes them to lose neutrality is a desire to have filled electron shells, or rings, if you will. If an atom does not have a full electron shell, it will choose to get rid or gain electrons. Truth be told, the description of atoms in your textbook is about 100 years old. It's known as the Bohr model of an atom, B-O-H-R. Modern chemistry talks about quantum mechanics, but to understand quantum mechanics, you must have calculus. And most of our students don't have calculus, so we don't start with that kind of description of an atom, okay? Suffice it to say, atoms are like people. We all have different personalities. Different thing, we respond to the same thing differently, right? I could tell you a joke, some of you would smile at the joke, other of you would not laugh at all about the joke because you have a different sense of humor, okay? Atoms are like that. Sodium has a personality that to become stable, it likes to eject an electron. Okay, so let me do it this way. Okay, I guess I can do that. It will eject an electron. Okay, 1 minus here. When that happens, I end up with 10 electrons around the sodium because it gave 1 away. Obviously, if sodium ejects an electron, the overall charge on the atom is going to go from neutral to what? What's going to be the overall charge on the sodium atom when it ejects 1 electron? Samantha, go ahead and speak up, Samantha.
+1 or 1 plus.
Okay, good job, right? Because we have 1 more proton than we have electrons. 1 more proton than we have electrons. Nicely done, thank you. So the overall charge on sodium is going to be +1. Okay, so I'll just put a +1 down here as the overall charge. Chlorine will accept the electron that sodium donated. I'm going to end up with 18 electrons here, which means the overall charge of chlorine is going to be a -1. And it's from this imbalance in the number of protons and electrons within each individual atom that creates an overall unbalance to the atom. The atom ionizes and becomes an ion. We go from an atom, which is electrically neutral, to an ion, which is an electrically charged atom. The electrically charged atoms, you've heard the old expression, opposites attract. When we create an opposite ionic condition of atoms that are nearby, they are going to be drawn towards each other, and this is the foundation of the attraction, which joins sodium and chlorine atoms together. Okay. All right, folks. Folks, are you okay? Is this making sense to you?
Yeah, it is.
All right. Okay. Any questions you'd like to ask? Okay, great. Well, then let's continue here. Turn this off. Yeah, right. Come on. Oh, I see what happened. Okay. All right. So, all right, I'm going to have to fix that document later. I will fix it and put it together for you in notes. I'm going to continue with a new document here. Let's describe the covalent bond next. Okay. Covalent bond. Okay, a covalent bond is an attraction created between atoms that share electrons. Okay, so in an ionic bond, you donate an electron, right? Sodium donated an electron to chlorine. That electron that's donated no longer orbits the nucleus of the sodium atom. But in a covalent bond, you share electrons. And by sharing electrons, you create a very powerful type of attraction. Okay, so covalent bonds are the talking points of figure 2.3 on page 29. And I want to point out to you that we can actually have different types of covalent bonds and use that as a springboard for a conversation. Okay, we can have polar and non-polar covalent bonds. Okay, and so let's draw this a little bit. Let me give you the polar scenario. Okay, polar means there's an unequal sharing of electrons. And well, let me see, maybe I should do the nonpolar first. Okay, I'll do nonpolar first. Okay, so nonpolar means there's an equal or even sharing of electrons. And a traditional classic example of this would be carbon-carbon bonds, carbon-carbon bonds. All right. So what I'm suggesting to you is this. If we have two carbon atoms that are participating in a bond, okay, it's like having a tug of war between two teams that are identical. It's like having a tug of war between you and yourself, between you and a clone of yourself, right? Imagine if you had a tug of war with a clone of yourself, that if you tugged on the tug of war rope, if there was a flag dangling down the middle, it probably wouldn't go anywhere because you'd be pulling in exactly the same moment with the exact same opposite force that the flag won't go anywhere. So when we talk about nonpolar covalent bonds, typically the analogy that's given or the visualization I would want to give you is to show you how the electrons are being shared. The electrons that are being shared between these atoms are shared in such a way, and I'm not a very good artist, that we have a roughly equal, yeah, that's not very good, a roughly equal amount of time of the electrons spinning around the nucleus of each atom. In other words, the electrons are spending 50% of their time around the left nucleus of the left carbon atom and 50% of their time around the nucleus of the right carbon atom. That's an equal sharing of electrons. The alternative to this, and I'm watching my time here because I know I'm almost out of time. The alternative to this is in fact the polar covalent bonds, where we have an uneven sharing of electrons. And an example would be a hydrogen-oxygen bond. So would be an HO bond. Let me give you an example of this, and then I'll wrap up. Here we have hydrogen. Here we have oxygen. And so the electrons that are being shared are going to be shared unevenly. And so the electrons being shared would kind of look like this. It would be a very unbalanced amount of time that's being shared here, so that the electrons might spend about 10% of their time around the hydrogen atom and 90% of their time around the oxygen atom. So I'm going to put a question in the chat window as homework for you. Here's my question. Okay. So don't answer it today, even if you know. Here we go. What characteristic of atoms that we discussed today can explain why polar covalent bonds form? What characteristic of atoms that we discussed today can explain why polar covalent bonds form? See if you can answer that on your own study time, and we'll just have a quick conversation about that at the beginning of next class to see if you understand why these things actually form. Okay. All right, folks, sorry I'm a little bit over, but no lab today. We have lab on Thursday, so I will stop here. I will tidy up the notes and I will send them your way, okay? So you will have them. All right. Do you have any thoughts or questions before we close up? I know, Elena, you wanted some time. I'm happy to do that. Okay. All right, folks. So have a good afternoon. We'll see you Thursday, okay?
Thanks, Dr. Allen.
Have a
Thank
good
you.
one.
Have a good night.
You too.
I am going to be sending the link back to the people that we started working with last week.
Awesome. Thank you.
Thank you.
I just had a quick question.
Yes.
So it is okay for us to work in groups, right? Like if